Module 8, the central nervous system. Ascending and descending pathways in the spinal cord. The reflex arcs you learned about in the previous section are extremely important, but you also need to know that the main function of the spinal cord is to be a conduit for messages from the brain to the peripheral nervous system and from the peripheral nervous system back to the brain. There are two pathways I want to cover that involve how information travels in this way. The first is a motor pathway. Motor pathways are called descending pathways because motor neurons are carrying signals from the central nervous system to the muscles. If you want to make a fist, you first think about it in your brain, and then action potentials are sent down the spinal cord to the muscles in the hand. In other words, the information descends from the brain down to the muscles. The second type of pathway is a sensory pathway. Sensory pathways are called ascending pathways because action potentials travel from the receptors up the spinal cord to the brain. Let's say you do want to clench your fist. Action potentials are initiated in the primary motor cortex, found on the precentral gyrus. If you want to clench your right fist, the primary motor cortex of the left side of the brain does the job. And because you're conscious of this action, it requires a direct path from the brain to the muscles. So only two motor neurons and an association neuron are needed to do this. Why is that important? Well, there's a close connection between what movements we want to do and how the brain then conducts those ideas to skeletal muscles. What happens is the neuron in the motor cortex, called the upper motor neuron, sends action potentials down the midbrain through the pons and to the medulla. There, the axons travel through the medullary pyramid. This is a spot where about 80% of the axons cross over. This is what's called decussation. The remaining 20% of the axons of other motor pathways cross over in the spinal cord. After the medulla, the axon travels to the part of the spinal cord where the spinal nerves are. These in turn have the efferent neurons that go to the flexor muscles, which flex the fingers. At the spinal cord, the axon synapses with an association neuron. That neuron then synapses with a lower motor neuron, which carries the action potentials to the neuromuscular junction of the muscles that need to contract. This is a pretty simple and direct pathway from the motor cortex of the brain to the muscle. There are 3 neurons and 2 synapses in this route: an upper motor neuron, a synapse to an association neuron, then a synapse to a lower motor neuron. This specific pathway is called the lateral corticospinal tract. It's called lateral because the axon travels down the side of the spinal cord. Corticospinal means that the route directly goes from the cerebral cortex down the spinal cord and to the muscle. All of your body has nerve pathways like this, so you can decide to move any of your skeletal muscles. However, the same motor neuron may get over 500 synapses from other neurons, so it can respond to signals about more than intentional muscle movement. It's able to respond to signals about muscle tone, posture, learned sequences such as typing or piano playing, and other actions. Now let's take a look at a sensory pathway. Sensory pathways are ascending pathways, sending signals from the receptors up to the brain. And there are lots of different sensory pathways. The example I'm going to use is called the anterior spinothalamic tract. Anterior refers to the fact that this nerve is located in the anterior or ventral part of the spinal cord. Spinothalamic refers to the signals traveling from the spinal cord to the thalamus. This tract can carry signals coming from gentle touch, tickle, and itch receptors. Let's say that a feather rubs against your skin. Receptors in the superficial part of the skin are activated, and action potentials are formed in the primary neuron. The axon diverges, each end forming a synapse with an association neuron. The association neurons each synapse with a secondary neuron. The axons cross over at the spinal cord, traveling up the anterior spinothalamic tract. The secondary neurons then go up to the thalamus and synapse with tertiary neurons. You see, the thalamus is a relay station for information coming from your sensory receptors, so this is why it can have some type of interpretation of the stimuli. But in order to fully understand what's happening, the signal has to be sent to the somatic sensory cortex, the location where the tertiary neurons take the signals to. In this pathway, there are 4 major sensory neurons to complete the link from receptor to conscious center. and there are 3 synapses as compared to the 2 synapses in the motor pathway. This is because sensory information has to be regulated and even sometimes inhibited. Remember when I talked about the sensory information that comes in telling you that you're wearing socks? That information needs to be dealt with to determine if it's necessary and if any action must be made. So that's why there are more synapses in the sensory pathway. The synapses can inhibit the formation of action potentials on the postsynaptic neuron, hence stopping unimportant information from bombarding our brain. But the conscious center of your brain is still aware of the information provided by touch receptors in case you really need to do something about it. For example, if your sock suddenly gets bunched up and you need to adjust it.
We certainly love computers, don't we? They can take in information, they can remember it, they can send it to other files or even other computers. They even correct our spelling and our grammar. Yet, as you've learned about the central nervous system, hopefully you can appreciate how complex a system it is. In fact, the brain is more complex than any computer network ever designed. It can send out signals through the spinal cord to thousands and thousands of effectors, and at the same time taking in and processing millions of signals coming in from all over the body, day in and day out. So when you experience a computer glitch, be grateful for how wonderfully and elegantly your internal computation and control center has been designed.